Alright, this is our compressed video experiment, elementary review of ordinary differential equations. Let me begin by saying algebraic equations determine points. For example, if we have two equations f of x and y equals 0 and g of x and y equals 0, then the graph of f and the graph of g may intersect at one or more isolated points, and those intersections are the solutions. But differential equations determine functions, and in particular families of functions. For example, this differential equation may have many such curves associated with it, and depending on initial conditions we will choose this one or this one. So the initial conditions make the solution unique and or can make them unique, and the differential equation then determines the solution. Differential equation can be of two basic types. One is ordinary differential equations where there is only one independent variable, so the derivatives will all be with respect to that variable. Over here it is x, second order, first order derivatives and so on. They can also be partial differential equations where in these examples you can see x and t are both independent variables and y depends on x as well as t. Y is the dependent variable, and you can have first order derivatives, second order derivatives and mixed derivatives. So here are some first order examples of ordinary differential equations. This is the separable case. So if dy by dx is a product of a function of x and a function of y, a special form, then we can separate it. Formally this g can be put here and this dx can be put here, and then we can integrate the two sides independently. This is a function of y alone, it can be integrated. A function of x alone can be integrated. It will give an integration constant, and we will have a solution, possibly an implicit solution. The linear case is a different example. Here dy by dx plus some function of x times y is equal to some other function of x. For this type of equation we can use an integrating factor. In this case the integrating factor is e to the power integral of p dx. So if p is some known function, you integrate it with respect to x, then you take e to the power of that function. Then what happens is you take this integrating factor multiplied with y. If you take the derivative of this product, you find that it is e to the power integral p dx times the left hand side of this differential equation. Therefore this thing must be equal to e to the power integral p dx times the right hand side of the differential equation. So if we integrate this product and add an integration constant, I am just reminding you, then what happens is that becomes equal to e to the power integral p dx times y. So then we multiply by e to the power minus integral p dx. That is the solution for this problem. Here is another peculiar special case. This is the case where the right hand side is homogeneous of degree 0. What does that mean? That means that if x is doubled and y is also doubled, the function value does not change, for example. So this is a quadratic term, this is another quadratic term, x times y, this is another quadratic term. I have put a cos of y over x here to help you realize that actually complicated forms are possible. Over here also this is quadratic, this is not, this is zero order, this is quadratic and quadratic. In this example, for example, if we say y is v times x, where v is a new unknown, then y prime is v prime x plus v. I put this over here for the left hand side, and over here what happens is when I put y is equal to v times x, I get x square here, x square v here and x square v square here. The x square goes common. Over here I get cos of v. Over here I have x squared and x squared v squared. That x squared is common. The x squareds cancel, and what I have left is a function of v only. If this v is moved over from the left hand side, then the right hand side becomes a function of v alone. I divide by x, and you can see that it is a separable case. Similarly, there may be other methods and tricks. There are different ways of solving different classes of differential equations. Sometimes we can't solve them, then we can solve them numerically if we can't solve them analytically. Please note that we could have systems of first order differential equations. For example, dy by dx is f of x, y and z. Here y and z are two different dependent variables. X is the independent variable. So along with this equation, we have another equation, dz by dx is some other function of x, y and z. These two are less easy, although they are first order actually, but they cannot be separated into, usually they cannot be solved using tricks like. Alright, let's look at second order ODEs. So they are generally harder. For example, here's a random example, y double prime, that is d squared y by dx squared. These two primes mean that. Y double prime plus 4x y cube equals 0. Let's just, then you can't separate these terms. If you try to separate it, you will end up with dy prime by y cube is equal to minus 4x dx. You see, and you don't know how to integrate this left hand side. So you can't try that separation. There is one useful trick which is reduction of order, and that you can try when the ordinary differential equation is not explicitly dependent on x. Here is an example. It's a made up equation, but you will see that there is no x here, there is no x multiplying it here. This cost depends only on y. X does not appear explicitly in this equation. So over here what we can do is we can introduce a new variable, this y prime, which is a function of x. We think of it as some new function p of y, and we are going to seek p. So if y prime is p, then the derivative of y prime of x, again with respect to x, is the derivative of p with respect to y multiplied by the derivative of y with respect to x. So this becomes p prime p, where I want you to remember that this y is a function of x, the y prime is a function of x, it is the derivative of y of x with respect to x. Similarly here p is a function of y, p prime is a function of y, and it is the derivative of p of y with respect to y. Y double prime is p prime p. With this substituted in here, we get p prime p, over here we get a p squared, and you see this is a first order differential equation, nonlinear with y as the independent variable, and you can now try your luck at solving this equation. In this particular example, if you notice that p prime p is the derivative of p squared by 2, then you see there is a p squared here, and it becomes actually a first order differential equation in the new variable p squared. And you can make some further analytical progress. Some of this will be seen in simpler examples in the class. Generally, solving higher order ODEs is harder. Okay, so this I'm just showing you this example and one trick here. And before I proceed to the linear case, I will comment on uniqueness of solutions. For this, there is something very important called the Lipschitz condition. I encourage you to read about it in a book. But here's what it is in a nutshell. If you have dy by dx is some function of x and y, then within some region of interest, what you need is f of x and little y minus f of x and capital Y, where capital Y is some other y. The magnitude of this change must be bounded by some linear variation. So what you are saying is this difference must be less than some finite number m times the difference between y and little y and capital Y. If the Lipschitz condition is met, then solutions are locally unique. If the Lipschitz condition is not met, for example, in this case, it is not met as we have just discussed, then solutions need not be unique. And you see that there is one solution, y identically equal to 0, you can substitute it, 0 here, initial condition is met. And the other one is y equals x squared by 4, not 2, I have made a mistake, I think this is 4. You can verify, it is x squared by 4. So what happens here is y equals 0 is one solution, y equals this parabolic variation is another solution, and in fact there are other solutions. It can remain 0 for some time and then climb in this parabola. The general nth order ODE is written like this. So the nth derivative of y is treated as some function of x, y, first derivative of y, second derivative of y, and in this way up to the n minus 1th derivative of y. I want to emphasize that we will always assume that the highest order derivative is known explicitly in terms of the independent variable, the unknown function, and all lower order derivatives of the unknown function. Okay. This is generally nonlinear and usually analytically intractable. It can't be solved analytically in general. The nth order linear ordinary differential equation is like this. It is the nth derivative plus some function of x times the n minus 1th derivative plus some other function of x times the n minus 2th derivative. In this way, some function of x, a n of x, let me write a n of x times y is f of x. Okay. This entire left hand side is called the homogeneous part, and it is called, formally it can be called L of y, where L is this operator. Given any function y, you can evaluate the left hand side, that's L of y. This right hand side is called the inhomogeneous term. Please note that these coefficients are variable, they are functions of x. The dependence of y is here, 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 like this, not inside this coefficient. The general solution of this equation, here the linear one, is the sum of two parts. There is a complementary solution and there is a particular solution. The complementary solution is the general solution of the homogeneous equation, L of y equals 0. That means it is the general solution of whatever you get when you remove this right hand side. Yp, the particular solution, is any solution of the original equation. See, finding the general solution is difficult. There are many solutions, many possible functions, but any one of them, if you find, that can serve as a particular solution, and you have to solve in general the homogeneous equation to get the complementary solution. This linearity of this ordinary differential equation lies in the fact that this L of y1 is, L of y is linear. For example, if there are two functions y1 and y2 such that L of y1 and L of y2 are both 0, then L of alpha y1 plus beta y2 is equal to 0 for all alpha and beta. This helps in superposition, it helps in solution methods, and this is the condition by which we say this left hand side is linear. Yc, the complementary solution, will have n arbitrary constants. Yp is any particular solution that you have found that does not have arbitrary constants. When you add these two, the general solution will have n arbitrary constants. Those have to be determined from initial conditions, ICs, or boundary conditions, BCs, and then a unique solution can be determined. Now we have come to the general nth order linear ODE with real and constant coefficients. These are easiest to solve, and that is why in your engineering courses there will be many of them. Here's the equation. This is similar to what we studied before, except a1, a2 and so on, they are not functions of x. The f of x remains a function of x. Recall that the general solution is a complementary solution for a particular solution plus a particular solution. For the complementary solution, we can try y equals e to the power lambda x, which means the kth derivative of y is lambda to the power k times y. Once we notice this, we substitute this expression into the homogeneous equation, that means by putting f of x equals 0, and this is what we get. We get this polynomial in lambda multiplying e to the power lambda x equals 0. Since this exponential is not 0, this thing inside brackets must be 0. This nth order polynomial has n roots including multiplicities and possibly some complex conjugate pairs as well. If all the roots are distinct, that means there are no repeated roots, there are no multiplicities are all 1, in that case there are k arbitrary constants that appear like this. You see, for every lambda it is a solution, so a linear combination of those is a solution as I described earlier, and so multiplying each of them by arbitrary constants and then adding them up gives you the general solution to the homogeneous equation. And if you have multiplicities, that means you have repeated roots. For example, if there are 3 repeated roots, then you will still take lambda star, let us say, then you will still take e to the power lambda star x, but now you cannot have c1 and c2 and c3, you will have c1 plus c2x plus c3x square. The reason for this is fairly routine, you can look it up in books. So you can see that still there will be 3 arbitrary constants. If there is a complex conjugate pair, let us say the r and r plus 1th roots are complex conjugates of each other, p plus minus iq, then instead of writing them like this with the cr and lambda r and cr plus 1 and lambda r plus 1, which is lambda r conjugate, when we write it like this, what happens is this is complex and these coefficients become complex. But instead of writing them like this, we can write them in the equivalent form, e to the power px. What is this p? This p is the real part of the root. And then a and b are two arbitrary constants that are replacing these cr and cr plus 1. A sin qx and b cos qx. And what is this q? It is the imaginary part of that root. In this way, for real problems, we will continue to have real solutions. Also in vibrations, of course, you will see that this is the exponential decay rate or growth rate of the solution, and this is the frequency of the underlying vibration. So there is an interpretation that is useful to mechanical engineers. But in either case, whether there is multiplicity, whether roots are complex, you can see always you will have n arbitrary constant. We have determined the complementary solution yc. To find the particular solution yp, some formal methods are described in books. Please look at them. Here I am talking about one simple method. So here is one example, y double prime plus 4y prime plus 7y is 2x plus 3. We can look at it and we can sometimes guess an answer. Remember that we just have to find any one solution. So this kind of method of guessing is perfectly allowed. So for example, for this problem, we may try yp is something linear in x, a plus bx, okay, guided by what we see here. So when we do this, I have already made a mistake here, apologies, this is b. So yp is a plus bx, yp prime is b, yp double prime is 0. When we substitute this here, 0 plus 4 times b plus 7 times a plus bx is 2x plus 3. We can separate out the constant part and the part which contains x, which is the same as equating the coefficients of x to the power 1 and x to the power 0. When we do this, we get two simultaneous equations which we solve for a and b. Once we solve for a and b, we have our particular solution. Here is another example, y double prime plus 4y is sine omega t. You may recognize this as a harmonic oscillator that is forced sinusoidally. We can try y is a sine omega t, where a is a fitted parameter that we have to find to make the solution match. When we substitute it here, the second derivative, y, the independent variable is t in this problem. When we substitute, we get minus omega squared a plus 4a times sine omega t is sine omega t. The sine omega t is not generally 0, so this thing has to be 0. Sine omega t is not equal to 0. This thing has to be equal to 1. And then a is 1 over 4 minus omega squared. And this works for omega squared not equal to 4. Here's another example. So this has some second derivative, first derivative, and just y. And here is some cosine term. And in this one, we can try y is a sine 3t and b cos 3t. The 3, of course, matches just this one. And once we substitute it and we equate the coefficients of sine 3t and the coefficients of cos 3t, we can solve for a and b. Suppose there are two different terms over here, we can find a particular solution for one and a particular solution for the other and add them up. What happens when we have this? Y double prime plus 4y is sine 2t. Then this sine omega t is not going to work. Similarly, if I have y double prime minus 4y is equal to e to the power minus 2t. Remember, the characteristic equation of this one is going to be lambda square minus 4, that equals 0. That means lambda is plus or minus 2t, plus or minus 2. And so over here, this exponent, this coefficient is one of the roots of the characteristic equation. When you have this, it doesn't work directly. What you can do is you can try terms like t sine 2t, t cos 2t, and for this problem, t e to the power minus 2t. Please try them and you will see how they work out. Here is the linear constant coefficient differential equation. We have found its general solution with n arbitrary constants. Now let us say initial values are given. That means y at some x, let us say 0, is given, dy dx is given at the same x, d squared y dx squared is given at the same x. Numerical values are given, all derivatives up to the n minus 1th derivative are given. Then we say this is an initial value problem. Notice that there are n conditions, they are all at the same x. Over here I have written x equals 0, but it could be x equals something x equals 1.5. All of them 1.5, that's fine. Then we will call it an initial value problem. What happens is that we have the general solution, in that we put x equals 0 and then we say that that is equal to 4. We take the general solution, we divide by x, differentiate with respect to x, then we put x equals 0 and we set that equal to 3. In this way we can get n simultaneous equations. Those simultaneous equations can be solved for the n arbitrary constants and they will give a unique solution for initial value problems, and this is the easiest easiest problem associated with this. When we have boundary value problems, for example, here is just an example, y may be given at 0, dy dx may be given at 0, but all the other derivatives may be given at some other instant of x, like x equals 3. In this case, we can usually still solve for the arbitrary constants. We can set up the n equations, that's not a problem. But we may not always be able to solve for them uniquely. Uniqueness is not guaranteed. So here is an example. Y double prime plus y equals 0 and y of 0 is given and y at some other x star is given. Looking at this, you may know lambda square plus 1 equals 0 means lambda is plus minus I, or you may just remember that the solution is a sin x plus b cos x. How to find a and b? From the boundary values. We can set it up as a system of equations. The matrix form is useful. What we get is a sin 0 plus b cos 0 is equal to 1. I am writing it as sin of 0 times a plus cos of 0 times b is equal to 1. Similarly, a sin x star plus b cos x star is equal to 0. I am writing as sin of x star times a plus cos of x star times b is equal to 0. This coefficient matrix, I am calling it P for the moment. A and B is the vector of unknowns or column matrix of unknowns. This is the right hand side. This will have unique solutions if the determinant of P is not 0, and the determinant of P will be 0 when sin of x star is 0. You can see that sin of 0 times cos of x star, that is 0. So the determinant is actually just minus sin of x star. So if sin of x star is 0, which will happen when x star is m pi for any integer times pi, in that case this does not have unique solution. It may not have a solution at all, certainly won't have unique. Here's a final comment. We can write higher order ODEs or systems of such ODEs as systems of first order ODEs. Here is some example, second order in y and third order in z. Like I said, the goal of the differential equation is to give you the highest derivative explicitly. So over here the highest derivative of y is the second derivative, the highest derivative of z is the third derivative, and these are given as some functions of x, y, first derivative of y, z, and derivatives of z up to but not including the third derivative. What we do here is we say y0 is equal to y, y1 is y0 prime, z0 is z, z1 is z0 prime, z2 is z1 prime, and in this way we go up including as many y variables as there are derivatives on the right hand side implicitly, meaning one less than the highest derivative. So over here y goes up to 2 derivatives, so here we go up to 1, z goes up to 3 derivatives, so over here we go up to 2. z2 being z1 prime, of course, is z0 double prime, you see that. Then what happens is now this one is one differential equation, this one is another differential equation, this one is another differential equation, this one is now a first order equation. Instead of being the second derivative of y0, it is the first derivative of y1, and the dependencies inside f are written in terms of x, y0, y1. So there aren't any derivatives in here. y0, y1, z0, z1, z2. Formally there are no derivatives here. Similarly, z2 prime is a function of all these other variables. So now if I say q is some column matrix of variables y0, y1, z0, z1, z2, you will notice that these 5 are the same as the 5 on the left over here, although the sequence is changed, it doesn't matter. Then we can say q prime is some new function, vector valued function f of x, the independent variable, and q. This is the first order system. This is very useful for numerical solutions, and I will specifically mention the linear constant coefficient case, which is q prime is aq plus b of x. So this b is a column matrix function of x alone, does not depend on q. The part that depends on q is coupled, all the components of q are coupled through some matrix A. This is a constant matrix, it is not an x dependent matrix. This I will discuss in class.